is A is 1 and B is 100. Let me magnify this a little bit more. No, I don't want to do that. But so in dimension n, okay, it has this even in this form n, okay, but n has to be an even number, so it's dimension 2, dimension 4, etc. So the idea of this is it's very cleverly built that it has a unique local minimum, which means it's a global minimum. And we can see that the last one is, so starting from the last one, we have this 1, okay? But the minimum is achieved at the next one being, like 1 square, so it's also 1, So its minimum is achieved at x1 equals 1, x2 equals 1, till xn equals 1, okay? However, the condition number, if we talk about the condition number of Hessian matrix at each step, it's super bad. Okay, it's almost like 1,000 or something. So now let's so here are some packages that we could use for our research. So you can use the code as a template to plot like surfaces. Okay, so first of all, in 2D, this guy represents a surface, and in 2D, this function represents a surface in 3D. So we could use these, so this is optional, this particular location is optional. So you can use M plus 3D and PLT to do things. So this is color map. But these are plotting, so these are importable plot. Okay. And the code you can use as a template as follows. So let's run these imports. Okay. And let's import torch. So this is kind of important. Okay, so torch set default type. Torch float 64. The reason to do that is torch by default is float 32, which is just called float or single precision. Okay. So we need, so this is float 60. So float 32 is basically we use 32-bit to represent a number. And because it's binary, so it ended up with only 10 to the -5 accuracy, which is pretty bad for, getting the optimization problem down. So, but it's somehow okay for neural network. Yeah. So float 64 is double, aka, so we'll use double precision. And so let's run this. All right. So now this is a very simple version of Rosenbrock function. It's using the famous lambda, this function in Python. So lambda is called an anonymous function. So let me explain lambda a bit. So what does lambda do is, for example, we can test lambda. Okay, so we can say f1 equals lambda. So once we type lambda in Colab, it says it's being highlighted, right? If we type lambda, yeah, there we go. So it has this autocomplete that, so it's like a special function. So for example, we type whatever symbol here, okay? So it's an input variable. So for example, we can type A, all right? Then after the semicolon, okay, we need to type what expression we want for a. For example, we can compute a function a squared, okay? And now if we do that, now if we print, okay, so if we print f1, and this a, okay, so this a here, so this a here can be anything. So for example, a here can be any. So this is the nice thing about an anonymous function is we think a is a number, but a can be anything. Okay, so a can be any type of variable that supports this type of operand. So for example, what we can do here is we can do approach a range, for example 5. So what happens here is, okay, so we have a range 5 is what? Is 0 to 4, right? 0, 1, 2, 3, 4. And then if we do square, we have 0, 1, 4, 9, 16. You know? So everything that supports this kind of operand will get printed. So for example, so we can even call indices. So right now, for example, we can do matrix. So lambda, let's change a variable, let's say s, okay? So we can do s is 0, okay, plus s1, all right? The simplest type of thinking is, okay, so for example, we can do print, let's see f2, all right? So we can do a simple list. For example, we can do 10 and 8. Then this will print like 10 plus 8, which is 18, right? Okay. Yeah, let me split. Okay.
So what's the difference between modal function? Because like previous session you talked about like how to define a function and just
like using def.
Yeah.
Something like this.
Yes.
Like this.
Yeah.
Okay, so I mean it's nothing that different. So that's a good question. So technically speaking, they are different objects. So this is what we call an anonymous function. So it allocates your memory differently, and so it doesn't have the flexibility, for example, to specify like default values. I don't know if Python 3.10 changes that, but so, and another is this can be very handily. So so if you read the code of some advanced, scientific machine learning or whatever, these code. So this normally serves as a very handy way to doing this map. Okay, but we have another map. Okay, so let me try this out. So filter code snippet map. Let's see if they have this map. That's too big. Okay, so yeah, but that's a good question. So so lambda, this anonymous function combining with map and can be a very handy tool in applying function to some sort of variables. So, but I haven't prepared some advanced example. So I got lazy. I rely on Copilot these days. And but we can. So let me try to see if GPT can give us some good answer. Oh, I can't use GPT here. Okay, let's try to use Google. Give me an example of lambda function with map. Yeah, it doesn't, okay. Anyway, so, but in summary, lambda is a very handy tool. So if we know how to exploit this syntax, it's very nice. So, and my point is, whatever this expression makes sense, we can call this function. So for example, we can call f2. We can even, for example, call matrix. So for example, touch, let's say I, all right, 5. Okay. So this is an identity matrix of dimension 5. So if we call that, okay, it gets us what? We add the first row with the second row. Okay. Okay. So this is lambda. So now let's read this. Okay. So this is how we implement Rosenbrock function. So for example, this is b equals 10, and we can even put a b here. So okay. So this is okay. This is okay. But we can also specify b before defining x. Okay. So this is literally the Rosenbrock function. We choose a equals 1 and b equals 10. So b equals 10 makes this problem not so bad. Okay. So let's run this code. And now, so these are some sample plotting code. So for example, this is initialized figure. Okay, so this is a figure. So we create a figure object, and this is an axis associated with this figure. You can think this is basically the coordinate system, and it has various settings. And then we evaluate this function in a linear space. So for example, our x is linear space from -2 to 2, and with 100 steps. And y is the linear space from -1 to 4, 100 steps. And then we build a mesh grid. Yeah, let me. So if we do that, okay, I shouldn't have split it. Maybe I should move this here, right? So what does mesh grid do? Okay, so let's print the size of x grid. So x grid, the size is like a torch size 100, but what about x size? Okay, so once we said we build a mesh grid, what does that mean? If we print the size, we'll find this is 100 by 100. What does that mean? So it's 100 by 100 matrix. So once we do mesh grid, okay. So mesh grid is doing tensor product. Okay. So mesh grid is doing tensor product, but as a tuple. So what happens is it produces all possible combination of xi, yi from this set xy and y. Okay. So what does that mean? So for example, this is a simple So let me do a simple example. Okay. So let's print torch mesh grid torch a range 2 torch a range 2. So what does this mean? So this is like a linear space. It's 0, 1, 2, and this is like a linear space. This is 0, 1, 2. So what happens is, yeah, let me still set, okay. So let's try to set, let's do this A1, A2, okay, equal this. And let's print A1 and A2. So this is how we like examine the code. When we see a code snippet, we can examine, you know, how it works by printing all the intermediate variables. So this is a very good habit to do research. Is we figure out what is the mechanics of this thing. We need, okay, so it changes behavior now. Anyway. Okay, so, yeah, I don't know why they want to add this. But anyway, so now you should be going, okay, there we go. Okay. So, what happens is it produces, okay, so torch A range is 2, is like a 0, 1, this is 0, 1, right? So what happens is it computes this tensor product grid so that, yeah, I should really bring my, oh, cool, thank you so much. All right. So for example, we have 0, 1, 0, 1, right? So what happens is, this is like A1 axis, okay? This is like A2 axis. And A2 axis has 0, 1 and 0, 1 as well, okay? Right? So now, once we do a tensor product of this grid, is we find the combination. So for example, then we have this point, this point, this point, and this point. Okay. So this point is 0, 0. This point, so A1 is 1, 0. This point is 0, 1, and this point is 1, 1. Okay. So everyone okay with it? Okay. So now what happens is, if we only look at these points, so 0, 1, right? So we only look at the point, we only look at the A1 coordinate, okay? We only look at the A1 coordinate. So it's gonna be, and we sort by dimension. So for example, this is our first dimension, okay? And this is our second dimension, so which is dimension 0. So if we sort by dimension, we'll have something like, so the first coordinate, it's gonna be what? Okay, 0, 0. Oh, its axis is in this way, okay? So first coordinate A1 is 0, right? And then the second point is 0. So the first matrix A1 tensor, okay? So we denote this tensor as this is 0, this 0, 0 here, and this 1, 1 here. And then A2, after being tensor product, is, we look at A2. Okay. So A2 first is 0, it's going to be something like this, so it's 0, 0. But A2 is like a transpose of A1. So in 2D, So in 2D, A2, this tensor product equals A1 tensor product transpose. So we'll have this 0, 1, 0, 0, and 1, 1. So this is how we build a grid. And then we evaluate. So what we can do is we evaluate our function on this grid, and then we'll get our surface. Thank you so much. Okay. So now let's do this grid. So for example, now this is like a 100 by 100 grid, and so for example, if we do that, we'll get our surface. Okay, so it looks like this. So this is our Rosenbrock surface. Okay, so basically the height of each point represents the value of this function, and it has this valley, this very narrow valley. So this is for b equals 10. For b equals 100, the valley is even narrower. Okay, and what happens is the unique local minimum, which is global minimum, is somewhere here. But the valley is so flat that the gradient is very near 0 along this valley. Okay. So what happens is if a point falls in here, the gradient descent struggles very much to get from here to here. Okay, because the gradient is so small each time. We're only moving a very small step. So we can even plot an interactive figure. Okay. So this is contour. This is contour. Contour is clearer. So if we do this, okay. So yeah, let me try to do 100. So it's just that these are kind of, I wanted this spaced out. Right now it's too dense. Okay, better. Yeah, maybe. Okay. So this is, let me try to change this to, okay, how about, let me change this to, this is a 16 by 9 ratio. So I mean, these are not to scale, but so these are contours or level curves we learned in the very beginning of our class. Level curve basically means at each, so on each curve, the function, the value is equal. Okay, so we can see the level curve is very dense here. Dense means fast changing. Okay, and then it's very flat here, almost no change, which means inside this region, the function value is within. So, for example, the increment here, so this basically divides equally of the function value into, so I just set the levels to 100. It divides the function value into equally, like 100 intervals, and it kind of calculates the change, right? Like here, it's like the change has no change with regarding like the change here, because this is within the change of like 100 divided by the total change. So, so which means it's very flat here. And okay, and we can even do this interactive figure. So for example, this cannot let me. Yeah, this I plot is interactive. Okay. So the A is azimuth angles, E is elevation. So for example, this computer is kind of slow. Come on, it doesn't change. Wow. Oh, every time it prints a new. Oh, this is Colab is kind of bad. I see. Okay, don't do this. Don't do this. Don't do this. So if you have VS Code, you can do this in the VS Code, but don't do this in Colab. Okay. So now we implement quasi-Newton method. Okay. So this is our quasi-Newton method we learned in using textbook. So I mean it's nothing fancy. So we have this initial guess. This is our initial guess for the inverse of the Hessian, and so if we assume we can evaluate gradient exactly, but in many of the cases we cannot. We can only approximate it. So today we'll use approximation. So in neural network PyTorch interface, in PyTorch neural network interface, it's using autograph. So today we'll just use something called finite difference, which we learned in calculus 1, which is just how we compute the limit of the derivative. So, I mean, this is our algorithm. So we'll talk about two algorithms. We'll talk about two things specifically. The first one is, in class, we assume we can do line search. I mean, this is actually for convenience. Okay, so we can do line search is for convenience. In reality, is normally we do an inexact line search. So we don't find the exact minimum along a line, instead we approximate it. So here we implement the Rosenbrock function. Okay. So this is a more formal implementation. So for example, by default, the dimension n is 2. By default, this b number is 100. Okay. And this is the finite difference to approximate the gradient. Okay. So the step size is by default is 10 to the negative 8th power. So let's run it. Okay, so here is a key step. One of the key steps is we do an inexact line search. All right. So the idea is so this is our descent direction. I have to add more. Okay. Two conditions is for 0 less than C1 less than C2 less than. All right. So yeah, let me add one more. So these are called Wolfe conditions. Yeah, I should have. So these are called Wolfe conditions, and the idea is we set a relative big size first. So in the code, I set it to be 1 first, and then if these conditions are not met, we decrease the step. This is a very natural thinking. So the first. Oh, I should have suggested. I think. So Nocido, right? So in the textbook, in the another textbook, Nocido and Wright suggested C1 is 10 to the negative 4. C2 is 0.9 for cosine. Yeah, I forgot where I see it, but I'm pretty sure this is the case, unless the textbook changes. But I haven't been reading that textbook for, I don't know, over a decade. But yeah. So, okay. The first condition is we check
function value is non-increasing, almost non-increasing. So that's why we choose C1 very small. Okay. So the idea is after we move to the new places, so this is like our xk plus 1. This is our xk plus 1. We basically remove in the descent direction. So we check this is less than f. So this is a linear approximation to it. So it's kind of asking us, okay, if this is a descent direction, we at least have to be on par with this linear function. Okay. So if it decreases faster, it's better. But it has to be at least, decrease as fast as this linear approximation. So, and we choose this kind of small because if this is an ascent direction, then this kind of prevents, this to the function value increase. Okay. The second is the famous curvature condition. The curvature condition is to prevent the steps being too small. So we don't want our step being too small because this condition, if f is smooth, is almost sure satisfied for sufficiently small alpha. Okay. So the second condition is to prevent the steps being too small. It's called curvature. So we have to at least guarantee that the curvature doesn't change too much. Because if the curvature changes too much, okay, yeah, but I mean, this is not tested. I don't want to get into too detail about this, but okay, so this is called curvature condition, and here is the implementation. I mean, so it's basically, so we have set an initial alpha, okay, all right, and C1, C2 is set according to Nocito and right. We evaluate, so we use this function as an input. We evaluate this function, and then we take the gradient. Okay. Then we compare the gradient with this. Okay. So this alpha is mathmol. So let me add one more line here. So this is torch matrix multiplication. So for example, so we can do a test. Okay, so we do A2 is torch random. Let's do 3. Okay, so A3 equals torch random 3, 5. Okay. So we do a result. So y equals, maybe not y. We'll use y letter later. So let's do A4 equals torch. Yeah, let's do A4 equals torch mathmol. These two multiply together. And then we try to do an A4 compare equals torch. Sorry, we just multiply these together using this at symbol. So this is also mathmol. So what we want to do is we print torch or close A4. So our hope is it prints true. So if these two tensors, their difference is within the machine epsilon limit, then this will print true. So it's true, So which means this operation and this operation for PyTorch, it's the same. Okay. So this torch or close is a nice way to do this equal. So So the other way is, so this is a more traditional way to do this. That is, okay. All right. But this thing is kind of bad, so don't do this. Okay, so this is backcoding practice. Just use their built-in function. So backcoding practice. So the reason why we don't want to do this equal. So the idea is, not recommended. So equal, using this equal. So equal basically says if these two are equal, it's true. Okay. However, not recommended for float or double type. Okay. So if a number is float or double, so this is like a typical like Google level 1 interview question. So there will be question like asking us, I don't know, but I interviewed Google like 15 years ago. But maybe the question changes and it may not be this easy. So, but these are like the basic of numerical analysis for like implementing an algorithm is never ever do this equal for a float number. Okay. But torch is kind of clever. It will print true as well. Okay. So as you can see here, so torch all just means, so this, by the way, this is a matrix. Okay. So this is a matrix. So if we print this guy, so this is a matrix, and torch all just means if the matrix, every entry of this matrix is true, then this will print true. Okay. So as we can see, every entry is true, and it will print true. Okay. So this coding practice is not recommended. To check if an operation is good, we should use this built-in function Oculus, and you can check its implementation if you're interested. It's basically considered all the cases. Okay. So now we do the line search. So the idea is basically we check the Wolfe conditions. Okay. So while these two are not met, okay, we do the following. So this is while these are not met, so we should use or, so it's like a logical negation. That's when, so now if the while loop is not satisfied, we exit the loop, so it means both conditions are satisfied at the same time. Okay. So now we do this. So here is our initial guess. Okay. So if we look back at the figure, all right. So we choose our initial guess. So we choose our initial guess somewhere around here. Let's see if quasi-Newton will take us here. Okay. Yeah, maybe I put the gradient descent comparison in the end, but you guys will see. So our unique local minimum is here, the global minimum is here. Our initial guess is somewhere around here, which is minus, okay. So which is right here. So this is our initial guess. That is minus 1.21. So this is the worst initial guess. And so this is setting up our dimension, which is 2. Okay. So this G is our initial gradient. Our initial guess for this approximation to inverse. All right. So this is identity matrix. So basically, this is a 2x2 identity matrix. And we set our iteration to be 1, so we record our iteration number, and we set our max iteration number to be 100. So we set a stopping criteria. So here, if the maximum iteration is reached, we exit the loop, and our exiting strategy is if the gradient is is greater than this number, so this is the norm of the gradient, which is the magnitude of the gradient. So while this is true, we perform quasi-Newton. Okay. And we print this at each iteration. So after each iteration is executed, we plus this by 1. I mean, this is just to replace our formula, okay, what we have learned, but in a compact way, so you can. So the line search is to figure out alpha. This is do an inexact line search. And this is exactly what we do. It's just we need a few intermediate variables, okay? Instead of implementing this one whole thing in one shot. So if we do that, okay, so let's try this. Okay, so let's see how many iterations we have. For example, right now, yeah, we're at 33 iterations. So this is our x. Okay. So the accuracy, I mean the local minimum is 1 and 1, right? So the relative error is 10 to the negative 6. So this is the 6 digits. Okay. And now let's check. Now let's check gradient descent. So this is a simple gradient descent algorithm. Same initial guess, and we use TQDM as a progress bar. Okay. So if the iteration, I mean, is greater than maximum iteration, we exit the iteration. So we compute the gradient. Okay. And we do the line search. This is the steepest descent. Okay. But with inexact line search, so we kind of monitor this change. So now let's try this. Okay. Remember, this is after like 300 iteration already, and it haven't reached a second digit accuracy yet. We have a sleep here. If you want to try in your, here is just for class demonstration purposes. You can remove this sleep, this pause 0.2 second. Okay. So after 1,000 iterations, the gradient descent almost barely break third digit accuracy for x coordinate, and it still is in second digit accuracy for y coordinate. So it's pretty bad, if you ask me. Okay. So this is a benchmark problem. And so basically, so this will be a sample code for our final project. So which I'll talk about next lecture. Okay. So that's it for today.